Hello dear viewers, I am your friend Shadab Imam and currently we are dealing with the topic of queuing theory under operations research. Today we are going to discuss the most important topic under queuing theory, that is model 1, also known as MM1 infinity model. And in this lecture we are going to see every detail of this model along with the complete analysis. So please be with us till the end, and if you are new to the channel, please subscribe the channel and don't forget to hit the bell icon. So let us move ahead, and before jumping on to the model, let us understand the state of the system. So basically there are two states of the system. First is the transient state system. A system is said to be transient state when its operating characteristics are dependent on time. And the second is steady state system. A system is said to be steady state when its operating characteristics are independent of time. So it is clear that in transient state, the system is dependent on time, and in a steady state, the system is independent of time. Now, usually a system is transient during the early stages of its operation, when its behavior still depends upon the initial conditions such as the number of customers in the system and the elapsed time. However, it is the long run behavior or the steady state condition of the system which is more important to us. And now let us understand one variable here. It is called traffic intensity or utilization factor. It is represented by rho. Now utilization factor shows that the amount of time the server is being utilized, and it is represented by rho, which is given by the ratio of mean arrival rate to the mean service rate, and mathematically it is represented as rho equals to lambda by s into mu. Here lambda is the mean arrival rate, mu is the mean service rate, and s here is the number of servers, and the unit of rho is Erlang. So for a single server model, we can see that the value of S here will be 1. So for a single server model, the utilization factor rho will be lambda by mu. For steady state condition, mu, mean service rate, must be greater than lambda, the mean arrival rate, and both lambda and mu are constant. So we need to understand that if the average arrival rate lambda is less than the average service rate mu and both are constant, then the system eventually settles down to a steady state, and the probability of finding a particular length of queue will be same at any time. And if the rates are not constant, if lambda and mu are not constant, the system will not reach a steady state, but it could remain stable. In a similar manner, we can understand that if the arrival rate lambda is greater than the service rate mu, then even if we utilize 100% of the server, then also we will not able to serve all the customers, and the queue length increases steadily with time, and theoretically it could build up to infinity, and such a state is known as the explosive state. So in this series of lectures we will assume the system to be in a steady state. Now let us understand the steady state balance equation. Let at any time n be the number of customers in the system, and consider a very small interval of time h, and during the time h we will assume that only one event can take place. Now that one event can be either one arrival or one service, or we can say no arrival or no service. Now the probability that there are n units or n customers in the system at the time t plus h is represented by this probability of n customers or n units at time t plus h. Now this can be achieved in several ways. So let us assume that at time t plus h we have n customers here. This can be achieved by one of the methods, such as at time t we have n minus 1 customers, and in a short interval of time h we have one arrival and no service. So that we have one event taking place here, which is one arrival. So after this one arrival, we have n number of customers or n number of units at time t plus h. In a similar manner, we can also achieve this if we have n plus 1 customer at time t, and in a small interval of time we have one complete service and no arrival here. So from this also we will finally get to n number of customers in time t plus h. And there is one more way we can reach n customers here, is that when we have no arrival and no service in a small interval of time h. So at time t we have n number of customers, and in a small interval of time we have no arrivals and no service, so that at time t plus h we still have n number of customers in the system. Now there is one more possibility arises, which says that there could be one arrival and one service. Now if that is the case, then we have two events taking place, one arrival and one service, which we prohibited earlier by saying that during the small interval of time at most we can have one arrival or one service. So that's why we will not take it into account, and we can take only these three conditions. Now let us see how we can write the equation for this. So the probability of n customers in time t plus h can be given by, now let us consider the first scenario where we have n minus 1 customers at time t. So here we have n minus 1 customers at time t, and in small interval of time we have probability of one arrival and the probability of no service. So here is one condition, and the second condition is when we have n number of customers at time t. So we have n number of customers in time t. Now in a small interval of time the probability of no arrival in time h and the probability of no service in time h. So we can see that there is no arrival and no service. And the third possibility is when we have n plus 1 customers at time t. So this is the probability of n plus 1 customers at time t, and with probability of no arrival and the probability of one service, we can have this probability of n customers at time t plus h. Now if we add all these probabilities, all the three situations, we will finally have the probability of n customers at time t plus h. Now let us move ahead and assuming that lambda is the mean arrival rate and mu is the mean service rate here. Now the probability of one arrival in time h can be given as lambda into h, and the probability of no arrival in small time h can be given as 1 minus lambda h, because we can either have one arrival or we can have no arrival, and the sum of these two is equal to 1. So once we have said that the probability of one arrival is lambda h, then automatically the probability of no arrival will be 1 minus lambda h. Similarly, the probability of one service is given as mu into h, and the probability of no service can be given by 1 minus mu into h. Now let us see how this equation actually carries out. So this is the complete equation here, and it may look complex, but if we analyze it properly it is very easy to understand. So let us understand this first part. So here, as we have discussed this is probability of n minus 1 customers in time t. This is probability of n minus 1 customers in time t. Here the probability of one arrival in small time h. So we know that one arrival is given by lambda into h. So this is lambda into h, and this is the probability of no service in time h. So we have seen here that the probability of no service is given by 1 minus mu h. So this is 1 minus mu h. Now let us understand the second part here. this is the probability of n customers in time t. So this is n customers in time t, and this is the probability of no arrival in time h. So this is the probability of, here it is, the probability of no arrival in time h, and it is given by 1 minus lambda h. So this is 1 minus lambda h, and the probability of no service in time h. So the probability of no service in time h is given by 1 minus mu h. So this is 1 minus mu h. Now let us move on to the third part. So in third part we have probability of n plus 1 customers in time t. So this is n plus 1 customers in time t, and this is probability of no arrival in time h. So this is probability of no arrival, which is given by 1 minus lambda h. So this is 1 minus lambda h. So this is probability of one service in time h. So this is probability of one service in time h, which is given by mu h. So this is mu h. So now I hope it is clear how this equation comes. Now let us move ahead and simplify this equation. So we have simplified this equation, and what we have done is we have neglected the higher order term of h. That means if we say the first part, this is lambda h, this is mu h. So if we say lambda h into mu h, we have h square. So we have neglected that term which is containing h square and above powers. So we have neglected that term. Similarly here, mu h into lambda h. So this will be h square, we have neglected it. Here also we have lambda h mu h. So this will be h square, so we have neglected that term, and our equation is reduced to this form. Now as we can see that the only term here which is without h is this one. So we have taken it to the opposite side. So this will be Pn t plus h minus Pn at t. So this is our equation. Now let us take h common here and take on to the other side. So this will be probability of n customers in time t plus h minus probability of n customers in time t divided by h. Now let us focus on this left hand side of the equation. Here we can see that the probability of n customers at time t plus h minus the probability of n customers at time t. So this is the change in probability after a small interval of time h divided by this time h, and this complete term can be given as the change in probability, that is a small change, which is dPn divided by the small change in time, which is represented by dt, and we will name this equation as equation 1 here. Now let us move ahead. So this is our equation 1, we have just write here. Now let us apply the steady state condition in this equation 1. And we know that in steady state condition, the system is independent of time. Now when we say independent of time, this means that the change in probability with respect to change in time is 0. That means the change in probability does not depend on time. So here this left hand side will be 0. Similarly, we can see here that the probability of n minus 1 customers in time t can be simply written as probability of n minus 1 customers, because now after applying steady state condition, the probability does not depend on time. So we do not need to write this t here, and this term can be simply written as probability of n minus 1 customers. Similarly, the probability of n customers at time t can also be written as simply probability of n customers Pn, and probability of n plus 1 customers in time t can also be written as simply probability of n plus 1 customers. Now let us put these values in this equation 1. So we'll have this equation reduced to this form, and now let us improve this in the form of probability of n plus 1 customers. So this equation has been reduced here, as we'll take these two parts on the left hand side divided by this service rate mu. So this is our new equation, and let us name this equation 2. Now in this equation 2, let us put the value of n equal to 0. Now if we put the value of n equal to 0, we will get the equation as p0 plus 1, that means 1. This is p0 mu plus 1 minus p0 0 minus 1. So p minus 1 into lambda by mu. So this is the equation when we put the value n equal to 0. Here there is no possibility of negative customers in the system. So practically there is no possibility or no chance of having a negative customer in the system. So what we'll do is we will neglect this term and we will write the remaining equation as it is. So this is the remaining equation here. Now let us solve ahead, and we have simplified this equation here. Now as we can see here that if there is no customer in the system, then there is no departure from the system. This means that if there is 0 customers in the system, then the departure, which is showing by p0 into mu, okay, this is the departure it is showing. So if there is 0 customers in the system, there is no departure. So the value of p0 into mu will be 0 here in this equation, and our equation will further reduced as p1 equals to lambda by mu into p0. Now this is very important result here, and now let us again put the value of n equal to 1 in the equation 2. So previously we have put the value of n equal to 0 in equation 2. Now let us put the value of n equal to 1 in the equation 2, and what we'll get is this. Here p2 will be lambda by mu into p1, and we have already find out the expression for p1 in terms of p0. So let us put this equation or this value of p1 in this coming equation, and we will have our equation as this, which is lambda by mu whole square multiplied by p0. Now if we put n equal to 2, then we will have this as p3 and lambda by mu to the power 3 multiplied by p0. Now after analyzing these equations, we can say that the probability of having n number of customers in the system is given by lambda by mu to the power n multiplied by p0. So this is the very important result here in this queuing theory, and we will repetitively use this equation in solving various problems. So please remember this equation. The probability of n number of customers in the system is given by lambda by mu, or we can simply write here rho. So this is lambda by mu to the power n multiplied by p0. Now let us move on to the model 1, which is MM1 FCFS infinity model. Now in previous lectures we have seen the Kendall's notation on which this model is being represented. Now let us again understand what this model represents. So let us see here, the first M here represents the arrival or inter-arrival distribution. So the arrival rate here, which is Poisson's distribution, and follow the Markovian property or memoryless property, it is represented by capital M here. Similarly, the second M here represents the service time distribution. So service time is exponentially distributed here, and it also follows the Markovian property, which is represented by capital M here. And next, the one here shows the number of server here. So this is a single server model and the number of server here is 1, and this FCFS is first come first serve, which is the service discipline we have studied earlier. And this infinity here shows the queue length. This shows that we are having the infinite queue length model, and the last infinite here shows the population or the calling source, and this model represents the infinite population model. Now let us determine the various parameter we need to use in this model. So the first one is that the probability that no customers in the system, or the probability that server is idle. Now this equation shows that probability of having n customers where n starts from 0 to infinity, or we can easily understand it as the total probability here up to infinity is equal to 1. So here we can see that probability of having 0% in the system, probability of having 1% in the system, probability of having 2% in the system, and so on up to infinity. And this complete sum is unity, or we can say 100%. Now in the previous results we have obtained expression for P1, P2, P3 and so on in terms of P0. So let us put these values here in this equation. So this is P0 and P1 is lambda by mu into P0. Similarly P2 is lambda by mu whole square into P0. Similarly P3 is lambda by mu whole cube into P0 up to infinity. So this is because of this equation we have derived just now. And now as we can see that here P0 is common term, so we'll take P0 out and we'll find this series. And if you look closely, this seems to be a geometric series here, and it is sum to infinity series. So starting from 1 lambda by mu plus lambda by mu whole square and so on up to infinity. So it is sum to infinity series, and we know that to find sum to infinity we use this formula which is given by a upon 1 minus r, where a is the first term which is 1 here and r is the common ratio. So common ratio here is lambda by mu, because lambda by mu divided by 1 is lambda by mu. So the value of r, the common ratio here is lambda by mu. So let us find the sum to infinity for this particular series, and it is given by P0 into 1 upon 1 minus lambda by mu. Now let us solve this. So this will be P0 equals to 1 minus lambda by mu, and we know that lambda by mu can also be represented as rho here. So it can be represented as 1 minus rho, which is the utilization factor. So from here we can say that the probability of having 0% in the system is given by 1 minus lambda by mu, or we can say 1 minus rho. So this is very important formula here again. Now as we can see here that the probability of having 0% in the system, which is the probability that the server is idle, is given by 1 minus rho. It is clearly understood that rho here shows the portion of time server is busy or utilized. Now let us see another parameter here, which is the probability that the number of customers in the system is greater than equal to n. So the probability that the number of customers is greater than equal to n is given by this, and we know that the total probability here is equal to 1. We have discussed it. Now what we will do here is we will split this into two parts, which is from 0 to n and from n to infinity. So let us do this. So here we have done this, and we have split this equation into two parts, from 0 to n and from n to infinity. And we can write this equation in this form, And from this equation we can see that the probability of having n person in the system where n is from 0 to n, and this is the probability of n persons in the system where n is from n to infinity. So this is equal to 1, and we need to find this particular term. That means we need to find the probability of having n number of persons where n is from capital N to infinity. So we'll take the other term on the right hand side, and this equation is simplified in this form. Now if we expand this series just as we have done in the previous parameter, then we will be able to find this equation, which is 1 minus P0 has been taken common out. So this is 1 lambda by mu plus lambda by mu whole square up to nth term. So previously it was up to infinity, so it was sum to infinity series, and here it is sum to n term. So this is sum to n term series. Now let us see here the formula for sum to n term, and it is given when r, that is the common ratio, is less than 1. So we know that our service rate, or we can say mean service rate, is greater than mean arrival rate. So the value of lambda by mu will always be less than 1. So the value of r is less than 1. That means we can use this formula here, where a is the first term, which is 1 here, r is the common ratio, which is lambda by mu, and n is given by this capital N, which is the n number of terms. So let us put this equation in this form. So this is the series, and we have put this into formula of sum to n term, and now we know that probability of having 0 customers in the system, this also is given by 1 minus lambda by mu. So let us put here 1 minus lambda by mu instead of P0. Now these two values are same, so they'll cancel out, and this equation now has been reduced to this form, and if we open the bracket here, we'll finally get this equation. And this is another very important result we have obtained here for the probability of finding n number of peoples in the system where n is from capital N to infinity. That means probability of having n number of persons which is greater than capital N. So it is given by lambda by mu to the power capital N. Now let us see another parameter, which is the average number of customers in the system. It is also known as length of the system and is represented by LS here. Now this LS is represented by this equation, which is 0 multiplied by probability of having 0 persons in the system, 1 multiplied by probability of having 1 person in the system, 2 multiplied by probability of having 2 persons in the system, and so on up to infinity. So if we add up all these probabilities, we will find the length of system here. And in short form, we can write this equation as this: n multiplied by probability of having n person in the system where n is from 0 to infinity. Now let us see here that probability of having n persons can be given by rho power n multiplied by p0. So we have seen this result previously, and this row is nothing but lambda by mu. So we have seen it in the form as lambda by mu to the power n multiplied by p0. So this is the same term here, and instead of lambda by mu we have put rho here just for the sake of calculation. Okay, so I hope this is clear. Pn is represented by lambda power n into p0. Now let us take out p0 and one of the row here. So we have taken out p0 and one of the row here, and the equation here reduced as this: n multiplied by rho power n minus 1 summation n from 0 to infinity. Now if we closely see this term n multiplied by rho power n minus 1, this form can be written as differentiation of rho power n. So if we differentiate rho power n, we will get this term. So we can write this term in the form of differentiation of rho power n. Now whenever we have a differentiation and a summation together, we can switch these two with one another. So we can have this equation like P0 into rho d by d rho of summation rho power n. Now again let us consider this particular value, which is summation of rho power n, where n is from 0 to infinity. So here again we have a sum to infinity term as we have done previously, and the sum here can be calculated by this formula: S infinity is equals to A upon 1 minus R. So sum to infinity can be given as 1 plus rho square plus rho cube up to infinity. So A here will be 1 and R here will be rho. So let us find this value here. So we can see here that our equation reduced in this form, where length of system is given by P0 multiplied by rho multiplied by differentiation of 1 by 1 minus rho. Now if we differentiate this 1 by 1 minus rho, we'll get 1 by 1 minus rho whole square. So let us differentiate this. So this is length of system, which is given by P0 multiplied by rho, and this is differentiated form, which is given by 1 minus rho whole square. Now we know that P0 can also be represented in the form of rho, which is given as 1 minus rho. So let us put the value of P0 here. So this is 1 minus rho into rho divided by 1 minus rho whole square. So 1 of the 1 minus rho can be cancelled here, and our equation is reduced as rho upon 1 minus rho. So the length of system here can be given by rho divided by 1 minus rho, and if we put the value of rho equal to lambda by mu, we'll finally able to get this equation as lambda upon mu minus lambda. So this is another very important formula which we are going to use to solve the model 1 problem. Now let us see another term, which is the waiting time in the system. So waiting time in the system is represented by Ws, and it is given by Ls by lambda. And if we put the value of Ls from the above equation, we'll simplify this equation as lambda by lambda mu minus lambda, and if we further simplify this, we'll find the waiting time in the system Ws as 1 upon mu minus lambda. So this is another important result we need to remember. So we'll need to see another parameter here, which is the average number of customers in the queue. It is also called the length of queue, and it is represented by LQ. So LQ here is given as average number of customers in the system minus average number of customers in survey. We know that the average number of customers in the system is given by Ls, which is nothing but the length of system, and the average number of customers in service is given by lambda by mu multiplied by 1. 1 here because here we have only one server, so it is a single server model. Now let us see how our equation shapes up. So LQ is equals to Ls, which is length of system, minus lambda by mu, or we can write it as Ls minus rho. And this is another very important formula we need to remember to solve model 1 problems. And let us move on to the next parameter, which is the waiting time in the queue. Now the waiting time in the queue is given by WQ, and it is equal to LQ by lambda. So here we need to remember this formula as LQ by lambda. So once we got the length of system, we can able to calculate the waiting time in the system, the length of queue, and the waiting time in the queue. Now after calculating the various parameters, let us find out the formulas we require to solve the MM1 infinity model. So this is important. Please keep note of this, that these are the 10 formulas we need to remember here. So the first one is the probability that exactly n number of customers in the system. So the probability of exactly n number of customers in the system is given by lambda by mu to the power n multiplied by p0. Now let us see the second formula. It is the probability that no customer is in the system. So probability that no customer is in the system is given by P0, which is 1 minus rho or 1 minus lambda by mu. Now let us see the third formula here, which is the probability that the server is busy or the utilization factor. So we have seen that utilization factor is represented by rho, which is equal to lambda by mu. Now let us see the fourth equation. Probability that the number of customers in the system is greater than equal to capital N. So this is given by lambda by mu to the power capital N. Now let us see the fifth formula. The average number of customers in the system, which is also known as length of system LS, it is equal to rho upon 1 minus rho. And if we put the value of rho as lambda by mu, we can find this equation in the form of lambda and mu also. Now the sixth formula is average number of customers in the queue. So average number of customers in the queue or the length of queue is represented by LQ, which is equal to LS minus rho. Now let us see the seventh formula here. The average waiting time of customer in the system. So it is represented by WS, waiting time in the system, and it is given by Ls by lambda, that is length of the system divided by lambda. Now let us move on to the next formula, the average waiting time of customer in the queue. So the average waiting time of the customer in the queue is represented by WQ, and it is given by LQ by lambda, that is length of queue divided by lambda. Now these two equations, the seventh equation, that is the average waiting time of system, and the eighth equation, average waiting time in queue, these two equations are the well known little equations. And the next formula is the probability that the waiting time in the queue is greater than time t. So here this we have not done previously, so please remember this formula. The probability that the waiting time in the queue is greater than time t is given by lambda by mu multiplied by e to the power minus of mu minus 1 into t. Now let us move on to the final formula we have. The probability that the waiting time in the system is greater than t. So here it is equal to e to the power minus mu minus lambda into t. So when it has been asked that the waiting time in the system is greater than t, we will write this equation, and when it has asked the waiting time in the queue, we will multiply lambda by mu, that is we will multiply rho here, and our equation will be done. Now after remembering all these 10 formulas, we will be able to solve all the problems regarding MM1 infinity model. So let us see one problem here, and the question here says that in a railway yard, goods train arrive at a rate of 30 trains per day. assuming that the arrival rate follow Poisson's distribution and the service time distribution is exponential with an average 36 minutes. Calculate the following. First, the average number of trains in the system. Second, the average number of trains in the queue. Third is the probability that the number of trains in the system exceeds 10. Now let us solve this. So the given value, that is the arrival rate, which is 30 trains per day. So arrival rate here is given 30 trains per day, and the service rate is given by mu, which is 36 minutes per train. So the service time is given as 36 minutes per train, and if we need to convert it, we'll see that in a day how many minutes are there. So there are 60 minutes multiplied by 24 hours, so this is the total number of minutes in a day, and we have 36 minutes required per train. So by calculating this, we'll find the service rate as 40 trains per day. So it can serve 40 trains per day, and the arrival rate here is 30 trains per day. So let us see and solve the part 1. Now the part 1 says that average number of trains in the system. So the number of trains in the system is given by LS, which is the length of system, and it is given by rho upon 1 minus rho, or we can use the formula as lambda upon mu minus lambda. So as we have lambda and mu as the value with us, so we'll use this formula. So length of system is given by lambda by mu minus lambda. So it is 30 by 40 minus 30, which is equal to 3 trains. So the length of system here is coming as 3 trains. Now let us solve the second part here, part B. Now part B says that the average number of trains in the queue. So we need to find the average number of trains in the queue, which is represented by LQ. That means we need to find the length of queue here. And this LQ is given by LS, that is the length of system, minus lambda by mu. So length of system we have already calculated in part A, which is coming as 3 trains. So let us put this in equation. So LQ, that is the length of queue, is given by 3 minus 30 by 40. 30 here is the value of lambda and 40 here is the value of mu. So this will come as 2.25 trains. So the length of queue here is 2.25. Now let us see the third part here. The probability that the number of trains in the system exceeds 10. Probability that number of trains in the system exceeds 10 is given by this particular formula, where the probability of having n customers from capital N to infinity. So we have already remembered this. This is given by lambda by mu to the power n. So the capital N here is equal to 10. So this is the formula. And now let us calculate this part. So this will be 4 by 3 to the power 10, and it will come as 0.0563 or 5.63%. So the probability that the number of trains in the system exceeds 10 is 5.63%. So if you find this lecture useful, please like, subscribe and share. Have a nice day. Thank you.